This is what the landing page looks like. There's a bunch of tools and examples that you can check out yourself. Just go over some of them briefly. More recent one is statistical analytics. You can select a signal, EEG. In this case, it will show you the spectrogram and histogram of the signal and calculate mean and standard deviation with upper and lower confidence limits. It will also calculate skewness and kurtosis, and most importantly, entropy calculation using different techniques. Another example is ECG signal. Get the raw data up there. It's the spectrogram, so you can see what the frequencies are predominant in the signal. It's a histogram. It will tell you if it's a white noise or stationary signal. You can also select your confidence levels for these calculations. And here it shows you the mean, standard deviation, skewness, kurtosis, and the entropy. So entropy is higher, meaning the signal is more repeatable over time. Some chirps. I don't know if this one is synthetic or not. This is more realistic. You get real noise, real chirps recorded from birds. So this is sound recordings. You get frequency components in there, a histogram and all the calculations. By the way, you can change the mode. Entropy is being calculated. A normal distribution, example of aneurysm, some sounds, ultrasound the bats make. This is obviously synthetic hopping between different frequencies. You can see that the distribution is not normal. This one vibration, I guess it's sound as well. You can see the distribution is skewed to the left, and on the right you see all the metrics for it. You can even plot the S&P 500. I don't know what period of time that is, but that's going up as always. The distribution is skewed as well, so not normally a distributed signal. In our example, reviewing EEG data, in this specific case it's 16-channel intracranial recording, so data from an implant. You can scroll through the data, look at some noise there, look what the signal is doing. Then you can change separation, so the signal amplitude becomes larger than all the channels become more overlaid. You can overlay them just on top of now, and this one shows that one of the channels is a bit slightly more noisy than all the others. And this is probably more useful. Split is by left and right, so we have 8 electrodes on the right side of the brain and 8 electrodes on the other side. So you can split them this way, which probably be most useful for further analysis. Another example, in this case, frequency response as well here on the right. This is the normal frequencies in EEG that we look at, that you can see the bands, frequency range down the x-axis there, and energy within that frequency band. You can scroll through that. Have some trending options. So currently it's being turned on. When turned off, it skews the signal, and the trending, normalizing it around 0 and flattening it out. So in this case, you can also see the difference. And you see when the trending is off, there's this low frequency component that goes away when the trend is turned on, because that's not part of the EEG. Just signal is drifting a bit, which is something that we want to remove. Again, you can go online and play with those tools yourself. They're on bionicsgears.com, and our one here. So the links on the front page, on the main page. Another tool there is another scroll through EEG, 16-channel EEG. In this case, though, it will display a spectrum. So this is frequency over time. There is an algorithm selecting the channel automatically. In this case, just going for the larger amplitude channel, so that will be that one there, the gray one, and it will show you its frequency components. Again, you can overlay them in different way, change your window size. In this example, just double the window 2 seconds and you see a spike there, but considering that channel is a bit noisier, you actually don't know if this spike is real, if it's actually coming from the brain or is it just some sort of artifact. So that's something that needs to be investigated further. So labeling is a big thing in EEG, especially for epilepsy. For epilepsy, normally you have a neurologist or EEG technician who is marking potential seizures, so spiking activity. In this case, just me marking examples of, in this case, baseline EEG, so nothing happening. And then you have some elevated alpha activity, elevated beta, delta. You can see what normally EEG will look like during sleep. Will be either delta or theta. And this more clinically relevant example where you have healthy patients with eyes open. This is what the frequency response looks like. And this is eyes closed. So you see not asleep though. But you see an elevated alpha, just different brain activity. In this case, the filter order is reduced, so all these bands are a bit more overlaid, one on top of each other. Again, this tool is available online as well. A general example of a feature extraction in images. So obviously it can be used for EEG or anything else. You can select your algorithm and it detects features in this image. So marking these curves by green and inner curves by red. This NAV algorithm does the same things. You get a lot of false positives. So false positives are those where the algorithm detects something but there's actually nothing there. So false positives there. And false negatives here where something was not detected. This algorithm making less detections, but say only one false positives and a bunch of false negatives for some reason more on this side of the image. So if you use something like this in EEG, you just have to be careful that none of the seizures or important bits were missed. So I used fuzzy logic a lot. Again, we normally use it for EEG signals. In this case, just a more general example where you have an input wave. You can add a level of noise and it will try and detect what signal was selected. And with this noise level, you get about 50% detection error. When you increase the noise further, you get 100% detection error. So essentially cannot make a detection. This specific algorithm cannot do that. And when you reduce the noise, detection error goes around 0. No, because there's still some noise in there. So noise reduction is a big thing in EEG as well. This is another example of a wavelet transform to try and reduce noise. So this is what the noisy signal looks like. And this is when the algorithm to remove noise being turned on. Another example, in this case, working a bit better, well, looks a bit better. So depending on the frequency of the signal, you might tune up your algorithm to match the different frequency bands. And another big thing in epilepsy research is being able to predict seizures. So we want to give a patient an indication as to when the seizure is about to happen, so they can, stop the car or get outside the swimming pool to keep them safer. In this case, so for example, if seizures hypothetically had these cycles throughout the day or week of when they're more likely to have a seizure or less likely to have a seizure, so you want with limited training set size be able to predict when they're gonna have a seizure next. So with this tool, you can change your training set size, see what difference does that make. So in this case, it's actually being indicated the goal have been reached is on the error trend. It has to be below 0.5, I think. So the previous one did indicate, well, the prediction does make sense, but the goal wasn't reached because this number is still considered large error. And when reducing training set even further, in this case, just making a prediction that the signal will be flat lining, the goal is indicated to be reached, and that's what performance of the algorithm looks like. And in other cases, like running the same thing, same conditions again, indicates that you have this oscillatory response. So that's the predictions made. It's highly confident in that prediction, but yes, just have to be careful because in different scenarios it will give you a very different answer, and you need to be able to interpret it into, ask an expert or just know all about it yourself. So this is the general architecture of my server. I'm using a GPU, doing a lot of manual labeling, mostly using fuzzy logic, but currently adding neural nets as well. Generally, the idea is that we take quality biomedical signal like EEG, calculate the amplitude, spectral H frequency, fundamental frequency, F node, and look at the left and right cross correlation or cross coherence in frequency domain. Mainly, again, using fuzzy logic and neural net to automate these things further. And yes, we have to ask experts what they think and get them to label some of the data. Currently, I'm restructuring the server a bit into slightly different architecture. Everything is hosted locally on Wurundjeri land. Coming up is a web API plotting cross coherence of different EEG channels. I have to correct that spelling mistake. And this is what it looks like. This is an example online available on matplotlib. So it's in Python. And I'll make something obviously better and display it in different ways. I got some ideas of how to do this. Another tool that is already available, just a synthetic EEG data generator. At the moment, it's just generating noise, but I'm working on injecting EEG feature-like signals into it. So, for example, you have your noise going, and then you hit this button, and it will inject a neural spike into your EEG. That's very useful because you can then test the hardware or test the algorithms that, for example, trying to detect those spikes. So you can actually test in a more lab environment how the algorithm is performing. Let me know if you have any questions. I have a YouTube channel where there's a bunch of videos now where I talk about this new project, the bionichaos.com. So essentially it's me either developing or testing it or describing what is it trying to do. I also live stream a lot so we can chat that way. I might just leave you with this.